Hi, everybody. Dr. White here, beginning the discussion of sequences in infinite series. We're going to start off talking about sequences. So I want to set up an example where you perhaps have a cake, and you're going to eat a little bit of it each day. On the first day, you eat half of it, okay? So like say you eat the bottom half, and so the top half is left over. And on the second day, you look at that top half and you decide to eat half of that. So you're eating like a fourth of the original amount of the cake. So that means there'll be like this little bit left over. And on this third day, you decide to eat half of that. So you're eating half of a fourth, you're eating an eighth of the original amount of the cake. And so you've got this little sliver left over. And then the next day you decide to eat, half of what's left. So you're eating half of an eighth. You're eating a 16th of the original amount of the cake. And some little bit is going to be left over. And you just keep doing that day after day after day forever. So what you get is a sequence of numbers that represents like how much of the original amount of the cake you eat each day. Half, and then a fourth, and then an eighth, and then a 16th, and a 32th, and so on forever. A sequence of numbers. Mathematically, a more formal definition of a sequence is it's an ordered collection of numbers defined by a function f on a set of sequential integers. And it's written with this slightly intimidating looking notation, curly braces, a sub n in the middle. So what does all that really mean? Well, like a set of sequential integers is a set of integers that are consecutive. They just got to start somewhere. For example, the set of integers that are all bigger than or equal to 1. Okay, so 1, 2, 3, 4, 5. That would be a sequential set of integers. 1, 2, 3, 8, 9, 10, 11, 12, and so on would not be sequential because it skipped some. You can start wherever you want, but you can't have any gaps. So like you could start at 3, 3, 4, 5, 6, and so on. That's sequential, but you just can't have any gaps. And if you got some function that you're going to apply to each of those integers, call it f of n, then you apply that function and you get what we call a term of the sequence, a sub n, okay? So in this case, for this particular sequence we've got up here, what if we let f of n be 1 over 2 to the n? And an is going to be f of n. Then a1 would be 1 over 2 to the 1, and that gives us the half right here. A2 would be 1 over 2 squared, giving us the fourth that we see here, and so on. And so we can think of the terms of this sequence as the ANs, okay? The AN is called the general term of the sequence. Different functions give you different ANs, and so you get different sequences out of them. So as far as the notation, you could write it like the general term AN with brackets around it. Or you could write the formula for the general term, like 1 over 2 to the n, the brackets around it. If you wanted to be specific about where you're starting in that sequential set of integers, then you could be specific. You could like write an n equals 1 at the bottom and an infinity at the top, and that's saying I'm starting with 1 and I'm not going to skip any integers and I'm never going to stop. Or you could, write the formula in the brackets as well. But frankly, we're often just going to be lazy, and we'll write the general term when we mean the whole sequence A1, A2, A3 forever. Or we might just write the formula when we mean the whole sequence, okay? So just give us that from time to time. So I stress again that you can start a sequence at any integer you like. You still have a sequence. So like if I take that formula 1 over 2 to the n and I start n equals 5, then I begin with 1 over 2 to the 5th, which is 132, and move to 1 over 2 to the 6th, and so on. That's perfectly good. That's still a sequence. So you can generate more examples by just thinking about general terms and thinking about where you want to start, like what your domain of integers is going to be. And then you could write out the terms of the sequence. So like, what if your general term an were 1 minus 1 over n? And what if you decided to start with a 1? Then you would have a 1 minus 1 over 1. That is a 0. A 1 minus 1 over 2, that's a half, and so on. Or what if you had the same general term, but you started at 2? Then you would start at the half and move on to the 1 minus a third, the 1 minus a fourth, and so on. You don't have to call your general term an. You could call it bn, cn, xn, I don't know. Here, the general term bn is sine of n times pi over 2. And hey, let's start at 0 for a change. So 0, 1, 2, 3, and so on. Sine of 0 pi over 2 is sine of 0 radians, which is 0. Sine of 1 pi over 2 is sine of pi over 2 radians, which is a 1. Sine of 2 pi over 2 would be sine of pi radians, which is a 0 back again. And sine of 3 pi over 2 would be a minus 1. Sine of 4 pi over 2 would be sine of 2 pi, which is the same as sine of 0, which is 0. So we're back at 0 again. And we can kind of tell this sequence here is just going to cycle 0, 1, 0, minus 1, 0, 1, 0, minus 1 forever. Say the general term is Cn is minus 1 to the n over n plus 1. And let's say we start at 0. So minus 1 to the 0 is a 1 over 0 plus 1 is a 1. I get a 1. And then the C1 would be minus 1 to the 1 over 1 plus 1. That would be a minus 1 over 2. C2 would be a minus 1 squared over 2 plus 1. That is a plus 1 over 3. And you can see that on the bottom, you're going to keep going up by 1. On the top, though, you're going to alternate between 1 and minus 1 because you're alternating between even powers of -1 and odd powers of -1. So if you want to get an alternation in the sign of your terms, -1 to the n is a great way to do it. You can also define sequences recursively. Recursive definition means you give yourself something to start off with, and then you give a rule for building new terms off of old terms. Like say I give myself this to start off with. Let's say I say that A1 is going to be 1, okay? And then I give myself a builder rule. I say, for n's bigger than 1, an shall be this, half of the previous term, an minus 1, plus 2 over the previous term, okay? So I could write out as many terms of the sequence as I wanted. Here's my A1, that's 1. Here's my A2 where I apply the builder rule. 1/2 times the A1, which was a 1, plus 2 over the A1, which was 1. Probably a good idea to simplify that, and it comes to 3/2. Simplification is useful because if you want A3, you've got to use the builder rule. It's 1/2 of the A2 plus 2 over the A2. Simplify that as 17 over 12. If you want A4, use the builder rule. It's 1/2 of A3 plus 2 over A3, and so on. So I don't have like a nice, simple, closed form formula for AN this time. Instead, I've got AN in terms of AN minus 1, a recursively defined sequence, a base and a builder rule. There is a notion of limit for sequences, just like there's a notion of limit for functions. In the textbook in Calc 1, you probably met the notion of limit for a function, and it was defined in terms of epsilons and deltas. And there was a more informal definition as well. The textbook is going to give you an epsilon-based definition for the limit of a sequence. I'm going to go ahead and give you the informal definition here. So we say that the sequence AN converges to a limit L, and we write that limit as n goes to infinity, AN equals L. We write that, or we write this, AN goes to L as n goes to infinity, if the following happens. The absolute value of AN minus L can be made as small as you like for sufficiently large values of little n. Okay, so the idea is you can get as close to, you can make AN be as close to L as you want if you go out far enough in the sequence, if you use large enough values of little n. Okay. So for example, let's take a sequence that has a limit. 1 minus 1 over n, that actually has a limit as n goes to infinity. What is it? Can we figure it out? Can we find the limit as n goes to infinity of 1 minus 1 over n? Well, one way is to think of it is to consider its relationship to a regular old function of real numbers, okay? Think about f of x is 1 minus 1 over x on the domain of real numbers from 1 to infinity, okay? So that half-open domain of interval of real numbers. Same formula, basically, as our sequence. If I were to graph f of x, here I have a graph just for x is bigger than 0. You got this curve is going up, and if I were to sort of throw onto that graph f of 1, f of 2, f of 3, f of 4, and so on, then I'd be throwing on 1 comma 0, that point, because f of 1 is 0. I'd be throwing on f2 comma f of 2, that's 2 comma 1 half. I'd be throwing on 3 comma f of 3, okay? Now, the sequence is these points, okay? The function is this graph. The function is leveling off closer and closer to 1. The sequence, because its points lie on the graph of the function, it has no other choice but to go to 1. Putting it mathematically, the limit as x goes to infinity of f of x is the limit of 1 minus the limit of 1 over x. That's a 1 minus 0. That's a 1. Therefore, the limit of the sequence has got to be 1 as well. What we're learning from this is that you can use everything you know about limits of functions to find limits of sequences, as long as you think about your general term for your sequence as being derived from an f of an x for real numbers, not just f of n for whole numbers. Okay, so looks like I've got a fire alarm here, so I think this is a good time to break off. When we come back, I'll look at finding limits for more sequences using this idea that you can relate it to limits of functions, regular real-valued functions. See you later.